Today is December 13th, 2011, and this is AP Statistics at Berkeley High School, and we're ready to start Chapter 8, Estimating with Confidence. So, today we're going to lay out the basics of what we mean by confidence interval. And then in 8.2 and 8.3, we're going to lay down particular procedures for estimating a population proportion and a population mean. But just like the video that you saw yesterday, went through some of these big ideas, we'll get the big ideas out of the way today. All right? So we'll need to, before we start getting to the nitty-gritty, we'll need to talk about what do we mean by confidence level? What do we mean by confidence interval in the context of a particular problem? We're going to learn how to describe what it means to have a confidence interval, give a range of plausible values for a parameter. We'll also review what parameter means in that section. We'll also talk about, as we did in the previous section, what conditions need to be met before we go and try to make these confidence intervals. And then also talk about the practical issues. That again was addressed in yesterday's video. Practical issues having to do with the trade-off between confidence level and margin of error, and also the practical considerations of sample size. So let's dive in. So one of the big ideas of statistics is that we like to get insights about what's happening to a population. We'd like to know, let's take some big issue. We'd like to know whether the world is getting warmer, because there are practical implications that go along with that happening. We'd like to know whether worldwide temperatures are higher. We'd like to know what the average worldwide temperature is. But we have the inability to measure the temperature at every location on the globe at all times. We have an impossibility of finding all that data. So what we have to do instead is we have to sample. We can't find the value for every location on the globe for every single moment of the days. So instead we sample. We take and we grab some of that data, and we're going to try to use that statistic number summarizing a sample to then estimate the number that summarizes the population. If we sample well, if we randomly sample, our sample should be unbiased. And the result that we get from that sampling becomes a good estimate of what's going on at the population level. But there's a problem with sampling. And the problem with sampling is I can sample twice and get two different numbers. If I sample 3 times, I'm actually likely to get 3 different numbers. Sample after sample after sample from a population typically yields different values for those statistics that we're looking at. Remember, a statistic is a number gathered from a sample. Those statistics could look like a sample proportion. I take a sample and I find what proportion are female. I take another sample, ask the same question, and the sample proportions are likely to be different. It's called sampling variability. The p-hats that we get from those different samples make up a distribution. The distribution of p-hats that we investigated in that last chapter. If I do the same question, I take a sample, I measure heights of people. I get an X-bar. If I do another sample using the same procedures, but using random selection, I'm going to get a different answer, a different X-bar. Multiple samples give us multiple X-bars, which give us a distribution of X-bars. Sampling variability is just part and parcel of what goes on when we do sampling. But each one of those p-hats, each one of those X-bars, is a reasonable estimate to the thing that we're really interested in. Am I really interested in what proportion of my sample is female? No. I'm interested in what proportion of the population is female. Am I really interested in what is the average height of my sample? Only in that it gives me insight about what the average height of the population is. Every time we sample, it's not trying to answer the question of what's the average of the sample. It's trying to get insight about what's going on at the population level. Chance variation makes sampling variable. But they vary in ways that over long terms are predictable. And that's the predictability that we're going to try to exploit in this chapter. All right. So, in this chapter, we are going to do two things. We are going to recognize that statistics gained from a sample vary, but they are reasonable estimators of the thing at the population that we're trying to estimate. And two, that those estimations, because of the regularity of the sampling distributions, those predictions, we can actually predict how far away we are from the real answer, from the population parameter. This process, again, is called inference. Inferring a result from a sample onto a population. Taking a little bit of data and then expanding and saying, this is what it means, this is what insight it gives us to a much bigger data set. So, let's take a look at this, this little activity that they have set up for us. I am going to go to my calculator, clear off this, and I am going to do what they just asked me to do. And then I'm going to try, under my list mode, I'm going to use the command mean, and I'm going to combine it with this new command I've never used before in front of you, which is the command rand norm. Right? And they want me to use the letter M. And letter M is right here. M, comma, 20, comma, 16. All right? Now let me tell you what that command is going to do for us. Okay, rand means random. Norm is for the normal distribution. This command is going to produce random numbers that fit from a normal distribution, meaning the things that are closer to the mean are going to be more probable than getting away from the mean. So a bell-shaped curve, things closer to the mean. The standard deviation of this random distribution that I'm pulling random things out of is 20, and 16 means I'm going to grab 16 items from that normal distribution. And when I'm all said and done, I'm going to take the 16 numbers from the rand normal, and I'm going to find its mean. All right? Now, I'm going to hide the screen from you for just a second, because what I want to do is, I forgot, but I am going to put a number into M, and I'm not going to let you know what letter M is being set to. All right? Of course, people who watch this recording later will know exactly, because they can see everything I did on the screen. Okay? Now, here's your job. Your job is trying to guess what the number I put into M is. When I hit the enter key, you see an X bar. You see a number that is 1, the average of 16 random numbers drawn from some normal distribution. What do you think my random number is? Answer? You don't know what my random number is. But what do you know? It's around 57. Is that okay? What if I hit and I get another 16 numbers, another 16 random numbers, find their average, and present that to you? What do you think my random number M is? 50? Why? The average of those two numbers. And if I hit again, maybe a little bit higher than 50? What if I did this again and again and again? Every single one of these numbers is a X bar. And if I took all of these X bars and looked at their distribution, we have a distribution of sample means, or at least the beginning of an estimate of one. Now, here's the world in which we actually live. Ready? In the real world, you don't get to see X bar after X bar after X bar. In the real world, what do you get to see? One X bar. And then you have to say, I think the real mean of the population is this. Let me say that one more time. In the real world, meaning in scientific research, in social science research, in marketing research, you get one X bar. And then you get to say, I think the real mean is, and then you have to fill in the blank. Now, that very first X bar that I gave you was what, 57? 57.3? How many people think that the real mean is exactly 57.3? None of you. Good. Let me change it again. How many people think that the real mean is around 57.3? Next question is, how close? Well, given that one number, pretend you didn't see all the other numbers, would you say it was within 1 percentage point? 10 percentage points. What we're going to do is we're going to work on that particular ID now. How close do we think that X bar estimate was? How close was it? All right. We want to skip this. All right. So let's go through the basics of this thing that we're going to call the confidence interval. If you only had one number to estimate an unknown population, you would probably use X bar. If you were trying to estimate the value of mu, if you only had one number with which to estimate mu, you would use an X bar. But what if you were trying to estimate the population proportion? What is the population proportion of people who are left-handed? What would you do? Would you interview everyone in the world, find out if they're left-handed? I'll say that again. Would you interview everyone in the world to find out if they're left-handed? No, why not? Too time-consuming. What would you do instead? Abby's like, I really don't give a care what percentage of the people are left-handed. Okay, Katya said SRS, meaning that we would do some simple random sample of the world's population. Ask them if they're left-handed. What's that? It would still be difficult. Even a sample would be hard, especially a simple random sample. But if we wanted to do that, we would then interview some sample, ask them if they're left-handed, and then when we find out what proportion of the sample is left-handed, we would give that name a p-hat, and then we said p hat is a good estimate of p, the population proportion. We call these ideas that we use x bar to estimate mu, or p hat to estimate p, we call them point estimates. Point estimator is a statistic, okay? Meaning it's drawn from a sample of a population parameter. A parameter is a value drawn from a population. Sorry, population parameter is kind of redundant. The value of that statistic from that one sample is called a point estimate, and ideally, the point estimate is a best guess at the value of an unknown parameter. It's a reasonable guess. It's only reasonable, by the way, if we use good sampling techniques, and the gold standard for sampling techniques is, of course, the simple random sample. Unfortunately, simple random samples are hard. Even the best technique is hard to pull off because it costs so much money. Or, in the case of things, trying to enumerate all the people in a population or the things in a population is really, really hard. Are mice getting smaller? Are the average weights of mice getting smaller? I don't know. How are you going to enumerate and give a label to every single mouse in the world? That'd be tough. They're so fast. Okay. Again, we realized from the earlier work that we did, the best estimators are unbiased, meaning that the center of their sampling distribution is actually the same as the population parameter they're trying to estimate. We also say that the best estimators have low variability. And we learned earlier the best way to get low variability is to have really large sample sizes. But even in the best of situations, low bias and low variability, there is still variability in our sampling, and we still won't know the exact answer, but only have a reasonable estimate. Can we go to the next slide? Yes? All right. So, in their example, they set their mystery mean to a value. They chose 16 random numbers and then found an X bar. And they came up with a value from one X bar, 240.79. And they asked a very logical question. That's an estimator. How good of an estimator? How close is it likely to be to the true mean? In this case, we know what the true mean is. They know it because they set the value m, and they set the mean of that population before they started creating those random numbers. So let's figure out how we can address the question, how close is x bar to mu? And we address that problem by looking at what would happen if we took not just one SRS but many SRSs of size 16 from the population. When we take many, many samples from the same population using the same procedures, we get a sampling distribution. Well, if we take all samples, we get a sampling distribution. If we took many, many samples, we get a good estimate of what the sampling distribution would look like. What do we know about the sampling distribution of X bars? Well, we know if the population starts out normal, the sampling distribution of X bar is also normal. And that's good for us. Why is it good for us? I'll try that again. If the population starts out normal, then the X bar, the distribution of X bar, the one that's made from all possible samples of the same size, and in this case 16, is also normal. I state that that's good for us, but I may be full of crap. Here's your time to tell me how full of crap I am, or to say, no, Mr. Fedor, we agree with you, and this is the reason why.
Mr. Fedor, we agree with you, and this is the reason why. It opens up a bunch of formulas we can use that we can.
There's a bunch of formulas that we can use having to do with normal distribution. We have 2 whole pages of numbers that we can use, but they're only appropriate to use if we're normal. That's good for us. I agree. I guess I'm not full of crap. Or maybe I am, but not about that particular item. Somebody else was like, all right. The other thing that we know about the distribution of X bars is where its center is. If we've done things well, the unbiased estimators, if that X bar is an unbiased estimator of mu, then the center of all those X bars is going to be exactly where mu is. And then lastly, the last thing we know about that distribution of X bars is that its standard deviation is given as sigma over root n, as long as the population is at least 10 times sampled. There's this idea that the underlying this formula of sigma over root n is the idea of independence. If we have independence, we're great, but most of the time we don't. Remember the cards example. Pulling cards out of the deck of cards changes probabilities when the deck is really small. But if the deck is really large, when we pull a card, probabilities change, but they change ever so slightly, and so much so that it's negligible. When population size is really big compared to sample size, we have essentially independence, and we can use these formulas. In this particular example, we're told that the standard deviation is 20, sample size is 16, and therefore the standard deviation of the X bars is 5. And that's good to know. We know its shape, we know its standard deviation, and although we don't know what mu, the population mean is, we know that that would be the center of the distribution of X bars. Again, idea. Far left-hand side, population distribution. Arrows in the middle represent multiple samples taken out of that population, and each of those X bars makes a new distribution, which we show on the right-hand side. We don't know where the center of that distribution is, but we do know that it's centered at mu, and we know that its standard deviation is 5. May I go to the next slide? All right. So, in their example, they got this X bar of 240.79. And we don't expect that to be mu. But we expect it to be near mu. We expect it to be a reasonable estimate of mu. So how accurate do we think it is? Is it within 100 points? Is it within 5 points? Is it within 1 point? How close is that X bar to the real answer? Well, in repeated samples, the X bars vary from mu with a standard deviation of 5. Now let me pull out some other ideas from this thing that we love so well, the normal distribution. I heart the normal distribution. I heart also not tripping over Kyle's back. If the standard deviation is 5 and the distribution is normally distributed, To me, that means that 68% of all the X bars are within 5 points of the true mean. I'll say that one more time. If the sampling distribution is normal and the standard deviation of the sampling distribution is 5, that means that 68% of all the X bars, although they will vary, 68% of them will be within 5 points of this unknown mu that we're trying to chase after. Knowing what we know about the normal distribution, I could also say this. 95% approximately of all the X bars that we could randomly pull are within 10 points of the real mean. Make a third statement. 99.7 of all the X bars that can be pulled out of that population will be within 15 points of the true mean. Where am I getting those numbers? 68, 95, 99.7. The normal curve has that attribute. Let's just hone in on the 95%. 95% of the X bars pulled from that population will be within 10 points of the true mean. We could say there's a 95% chance that the 240.79, there's a 95% chance that that particular X bar is within 2 standard deviations of mu. I could say then, not with 100% surety, but with a 95%, and I'm going to use the word confidence, that 240.79 plus or minus 10 is where the true mean is. Let me draw that picture. Here is the distribution of X bar. Here's it centered at mu. Here's me going on 2 standard deviations either side and capturing 95% of all of those X bars in that interval. And that interval is plus or minus 10, going 10 down or 10 up. Here's an X bar that I just grabbed. Now, could that X bar that I just created, could it be here? It could be. Could it be here? It could be. Could it be here? Could this X bar be way out here? It could be. But what? But probably not. It's not one of the 95%. It's one of those strange 5%ers. 95% are going to fall in this range. Whoops, not that range. Where's one that goes 2 standard deviations up? 95% of the X bars fall within that range. That other one that I drew, it could happen, but it's Not likely. Now here's the interesting thing is, I still don't know what that mystery mu is. But I do know this, that if I go out 10 points on either side of mu, I capture a lot of x bars. And the same thing is true is if I leave x bars and I go 10 points out, I'm likely to capture mu. Okay? See how wide 10 is? About a pen's length? If I go a pen length out from x bar, the interval plus or minus 10 points has mu in it. My x bar plus or minus 10 contains the unknown mu. How about this one? I go a pen length out either side. That interval captures mu. How often will an x bar capture the mu? As long as it's within 10 points of mu. How often does it happen in this particular case? 95% of the time. Using this procedure, 95% of the time, my x bar estimator, plus or minus 10, has in it the real answer. Oh, but what about this one? What about this guy over here? Sad face. What happens if I use that x bar? Sad face. I am trying so hard to make this interesting. You guys are so sleepy. Am I just rambling? Okay, then let's take a step. Then let's take a step. And let's take a step back. I'm going to go back so it doesn't sound like blah, blah, blah. All right? I really do. All right? I can't go back to day one in this class. But I know that you know stuff. All right? I know that you are interested in what are you interested in? I will build an example of the thing that you are most interested in. Name it. I know you are interested in Marquise. My sampling gives ample evidence. All right. Okay. So I'm going to make up a Marquise question. It's got to have a numeric. It's got to have a numeric. Oh, this is all I can think of is lame things like what is Marquise's favorite number? That's what I mean. Okay. Because you are interested in all things Marquise, you want to know exactly how much he weighs. This is lame. I know this is very lame. All right? But the problem is, you know what? Marquise doesn't weigh the same every day. Do you know that? I mean, all of us have weight and our weights vary. That's true? No. Okay, all right. So, but over every single moment of Marquise's life, which you are intimately and infinitely interested in, you want to know exactly what his average weight is. Right? Can you imagine that? Being so interested in him that you got to know exactly how much his average weight is. Okay, so it's a silly example, but I'm trying to, again, I want to do something that'll make sense, help you make sense. Now, can you have Marquise standing on a scale every moment of the day with you writing down what his weight is every moment of the day? No. That would be silly. How could he get to class? standing on a scale every moment of the day. So you, instead, say, I'm just going to have him step on the scale at random times of the day, and I'll write down his weight. Is that okay? Maybe you do 16 of them. Is that okay? And those 16 weights, are they a statistic or a parameter? A statistic, says Dan. He's trying to help you out because he's well, who doesn't love that? All right. So, Danny says, when you weigh him at 16 random times, that's called a sample. And the number, the average weight that comes out of that sample is called a statistic. And that statistic, although not a perfect estimate of Marquise's weight, it's a reasonable estimate. It gets you in the ballpark. Because as you fill out your little Marquise scrapbook, all right. Now, let's make some assumptions about Marquise's weight. That it's normally distributed. It's a bell curve. And actually, normal distributions show up naturally in so many things. That's a reasonable assumption. And Michaela, you love normal distributions, don't you? You know how to use a Z table. I've seen you do it. So you love normal distributions, like me. Second assumption. Somehow, and this is the one that's totally false, somehow we know the standard deviations of the variation in his weight. We really don't, but we're going to pretend we do. All right? All right. If we know those two things, we take your estimators, we take your sample of his weights, and somehow we're going to get a little bit of insight about what his true weight is. We're going to be able to we're going to be able to say that we have a really good feeling, a lot of confidence that we know the range in which his true weight is found. Now, why don't we know his true weight again? Because Marquise has got to go to class. He can't be standing on a scale all day long. So we can only have him stand on a scale sometimes. Okay? Am I still just making blah blah noises? A little bit. Where did I lose you? Tell me where he's like, I had you had me up to this point and then you went off the cliff. I think you're just giving me the... All right. Here's what we say. If somehow magically we knew that the standard deviations of Marquise's weight distribution was 20, and if you weighed him 16 times, then we've got that formula that we used on the previous test, sigma over root n. The distribution of all the possible x bars, of all the possible sample weighings of Marquise that we could have, average of all the samples, would then vary away from his true weight by plus or minus, or by a standard deviation of 5. His true weight is right here. I'll put a little heart around it for you, Michaela. His true weight's there, and all the little sample weights that we could take has a standard deviation of 5 away from that true weight. And because we know the 68, 95, 99.7 rule, we know that 95% of them are going to be within 2 standard deviations of that mean. 95% of those those sample means are within 10 pounds. So if you weighed him 16 times and you got a weight of, I'm going to play a guessing game, 145? You're heavier than that? 20 pounds heavier? You got a lot of muscle then. Yeah. Okay. So we do those weights, and we get a weight of I'm going to go 162 because it's an estimator. All right. And what am I saying? That 162 has a 95% chance of being within 10 pounds of his real weight, his true weight. Now, when Danny weighs him 16 times, he's going to get a different X bar. Now, he's doing it on the slide. You don't know about it. He gets 16 of his own weight. Does he get 162 as well? Probably not, because what is the thing? There's this thing called sampling variation. But you know what? His X bar also has a 95% chance of being within 10 pounds of the real weight. Of course, you don't know that I'm also secretly weighing him. There's a little scale built into his chair. And the moment he leaves, after every single class day, I go rush over to see how much does he weigh today. And I got an X bar. Is my X bar going to be the same as Danny's? Is my X bar going to be the same as Michaela's? No. But my X bar is just one more estimator, and there's a 95% chance that my X bar is within 10 pounds of the real weight.
What's Danny weighs without clothes? Isn't that like 2 pounds?
All right. Now, how often are we going to be wrong? Marquise with his 20 secret admirers, all secretly weighing him. How often are we going to be right? How often are they going to use their sample weights, add plus or minus 10 pounds, and have a range where his real weight is? How often are they going to be right? How often are they going to be wrong? And the answer is, since 95% of the X bars lie within 10 points of the true mean, 95% of the time, the interval that we create with the X bar in the middle is going to capture the true mean. 95% of the time, the X bar is going to be close enough. 5% of the time, it's going to be sad face. 5% of the time, the X bar is going to be improbably away from the true mean. It happens. But you know what? If I could lead my life and be right 95% of the time, I would be a very happy man. If I could get up to 50%, I'd be a very happy man. If I could know the truth 95% of the time, that's a really, really great thing. Okay. So here is the summary of all that idea. 95% of all the samples of size 16 from the population of Marquis' weight, 95% of the samples will lead to averages which are plus or minus 10 points of the real unknown weight, his true weight, his population weight. We say that the interval centered at X bar, centered at Danny's sample, or my sample, or Michaela's sample, the interval centered at that and going 10 points below or 10 points above captures the true mean 95% of the time. We call this idea that I created a range of numbers and I'm right within that range of numbers, the true mean is, we call that 95% confidence. We say that I'm 95% confident that when I weighed him and got 160, plus or minus 10 points, which is a range of from 150 to 170, I'm 95% confident that that range from 150 to 170 really has in it his true weight. Could I be wrong? Yeah, using this procedure, I'm wrong about 5% of the time. But using this procedure, I'm right 95% of the time. And again, we call that being 95% confident. Okay. In this particular example, with the mystery mean, they did one X bar. They got 240.79. They took the standard deviation of 5. They doubled it to match the 95, the 68, 95, 99, 7 rule. And what do they say? Oh, we have a range from 230.79 to 250.79, and we have 95% confidence that the true mystery mean lies in that range. What does that mean again? 95% confidence that if we use these procedures again and again and again, 19 times out of 20, we're going to have the right answer. Hey, what if I want to be 100% confident?
That sucks.
If I want to be more confident, I need a bigger range. If I want to be 100% confident that I can guesstimate Marquise's weight, I'm going to have to go from 100 to 300. I'm 100% confident that he weighs between 100 pounds and 300 pounds.
Yes.
I have a big range. If I want to be less confident, I can have a narrower range, but of course I'm going to be wrong more often. I'm going to be wrong more often if I'm only 68% confident. But I'll have a narrower range. In the video yesterday, that was the trade-off that the professor was talking about. The trade-off between having a smaller range, and we call that range, by the way, a margin of error, and being more confident. Okay, so here's the basic formula. Here's the basic procedure that we're looking at. We sample. We get a statistic. That statistic is an estimate. The estimate is not the thing that we're looking for, but it is close to the thing that we're looking for. How close is it? We say it's within a margin of error. How do we calculate the margin of error? It's plus or minus some amount, and that amount's related to two things. The margin's related to two things. How confident do we want to be in our answer, and how much variation is there in our sampling? So, confidence interval, the thing that we're trying to create, has two parts. The interval that we actually calculate, and how confident are we that we're in that interval? In the example I've been doing with Marquise, I said from 130 to, not 130, 140 to 160. That was my confidence interval. Ranging from 140 to 160, and how confident was I in that answer? Well, based on a bunch of assumptions which probably aren't true, I am 95% confident in that answer. We call that 95% part the confidence level. The confidence level. So whenever we say a margin of error, we also have to say at what confidence level are we working with. Want more confidence? You need more margin of error. You want to be wrong more often? You want to have a lower confidence level? You can have a smaller margin of error. mean. What do we mean by that confidence interval? If we use this procedure again and again and again, the confidence level is the percentage of times that our confidence interval actually captures the true mean. Everyone got all this down? No? By the way, when does this get used in real life? Answer? It gets used in real life in political polling.
And stats class.
Stats class is not real life.
It's real. This isn't real.
Okay.
It's like a video game.
When they do political polling, don't you ever hear them saying these poll results are accurate to plus or minus 3%?
Outside of that.
Isn't that over 3% of that?
What they're saying is there's a margin of error. They think the real answer is within 3 percentage points of what they just published. What confidence level do they use? And the answer is they use a 95% confidence level. Right? I am going right to the end. I'm glad that all of you are so interested in being on time for your next class that you're starting to pack up, but I'm going right to the end. Okay. Typically, we want to be right at least 9 times out of 10. Typically, confidence levels are set at 90% or higher. Typically, newspaper polls have a 95% confidence, so they're right 19 times out of 20. Okay. Nope.
He's so crazy, like he's a cat, but like he hates humans.
Okay. I think we covered all these ideas. Let's get to this box part. Okay. One more time. To say that we're 95% confident is to say that the confidence interval created using these procedures captures the true parameter 95% of the time. That doing this many, many times using the same procedures, 19 times out of 20, we capture the unknown parameter. The unknown parameter could be a mean, like Marquise's average weight. Could be a proportion. Well, population is left-handed. All right? So if you are asked a question like, interpret C% confidence. We say we are C% confident on an interval from blank to blank. That within that range, we capture the true value, that population parameter. All right? Okay, I've already said that. A lot of the things that are in here, I've already said, but this is probably the last thing I'm going to get in. Okay, I want to give you a warning. There is a trick, there is a trap in the questions on this chapter and on the AP exam, and I want you to not fall into the trap. We use the word confidence interval. No, I got to get this in. Okay, we use the word confidence interval. We never use the word probability to describe that 95%. We don't say we have a 95% probability that we capture the true mean. The reason why we do this is long, and I don't have time to explain it. But if you ever see the word probability used with the word confidence interval, it's the wrong answer. All right. Do your homework. Bye.